9 a.m. and we can continue. So, in the previous, up to this point, what we've been doing up to this point in terms of solving problems, every time we used electric force and electric field, and they worked great. Nothing wrong with them, right? So we could use them to solve any problem from the world of electricity. But they are vector quantities. And of course, dealing with vector quantities is not kind of fun, right? Because you have to take care of magnitude and direction. And it can be really, really tedious, right? Depressingly tedious. So of course, as a result, of course, it would be quite a natural idea. Can we replace vector quantities with similar scalar quantities? Right? So that's what I wrote. Can we replace vector quantities with scalar quantities? And as the first step in this replacement, in the previous lecture, we substituted electric force with the electric potential energy. And as I told you, these quantities must be similar. It means that they must describe exactly the same thing. What do I mean? In this case, force. Force, you remember, it was introduced in physics to describe any possible interactions, right? And potential energy, it is an energy of interactions. Basically, these two quantities, right, different quantities, they basically describe exactly the same thing, interactions. If there is an interaction, if you want, you can describe it using electric force, or you can use potential energy, right? Okay, so that was the first replacement. And as I said, potential energy, it's an energy of interaction. So you must have at least two objects which interact, right? All right, so, and we're going to discuss as a result, we will be discussing two systems, okay, of two objects, right? First system, it's a point charge in a parallel plate capacitor. Basically, point charge exposed to a uniform electric field. That will be the first system, and the second system will be two point charges. So let me write, of course we discussed that in our lecture, and now let me just write down the expressions which we need to use, and of course we need to understand the meaning of each quantity in those expressions. Right, so which way I wrote it? Two systems, right? Two systems, right? So the first one, which way I wrote? A charge inside of a parallel plate capacitor, a PP capacitor, right? Okay, so let me draw the picture. All right. So let's say this is my one electrode. Here's the second electrode. Let's say this is negatively charged. Let's say this is positively charged. Of course, there will be electric field, right? And of course, charge, right? System of two objects, capacitor and the charge. Of course, we can introduce potential energy because they interact. Then we also need coordinate system. So letter S is used in this book, at least, so I tend not to change notations. This is the origin, S equals 0, and this is spacing between the plates of this capacitor D. So as a result, we derived formula for this system. Potential energy, in this case, maybe I will, let me write it here. U equals Q times E times the distance from the negative electrode. So let me frame it, because it's a potential energy of this system when a charge Q, point charge Q, is exposed to a uniform electric field E. And look, charge can be positive, can be negative. So it can change the sign of the potential energy, careful. Electric field, it's an absolute value. If you remember how we derived it in the lecture, electric field over here, it's an absolute value of the electric field, just a positive number. S is the distance from the negative electrode. Right. Also, in the lecture, I told you that the reference point is very important. To know where the reference point is very important. In this case, the reference point is at the negative electrode. It's a point where the potential energy equals to 0. Right? Maybe I should write this. This is the point where U equals 0. So that's the reference point. Maybe I should write ref point. Okay, so we're going to use this. And you know what? Let me also plot, for example, potential energy versus position for a positive charge. Let's say for plus Q. If you have a positive charge, potential energy, of course, is going to be positive, with 0 at the negative electrode. When S equals 0, of course, the potential energy is 0. So if you plot potential energy versus S, it will be something like this. It's for a positive charge. But of course, if you have a negative charge, minus Q, right? And if you plot something similar, so again, this is potential energy versus S. In this case, since charge is negative, there will be minus in front, basically. Right? So 0 again at the negative electrode, and after that, potential energy goes to negative values. So that will be the plot if you work with negative charge. Okay, so we're going to use this system, and the second system, 2-point charges. Again, guys, if you need some additional explanations or clarifications, just tell me. 2-point charges. Right. Okay, so let me draw it here. So what if we have charge Q1 and Q2? Okay, Q1 and Q2 at the distance r, then potential energy in this case, U equals K, product of two charges, Q1 and Q2, and divided by the first power of r. Again, that is the scalar quantity, so it doesn't have directions. Right, let me frame it. And where is the reference point? Again, the point where this potential energy goes to 0. When r goes to infinity, potential energy goes to 0. Right. So let me emphasize. So the reference point, basically U equals to 0, is at r equals to infinity. Okay, let me check what else I wanted to mention. Okay, so the last piece of an introduction, let me put here a new bullet. So now, what if we want to, for example, describe motion of some, I don't know, charge, describe behavior of some electrical system. So now we can use this potential energy in collaboration with kinetic energy and under a roof of a conservation of mechanical energy. So basically now we will be using conservation of mechanical energy to describe behavior of electrical systems. Let me write. Right. So now conservation of mechanical energy. So which is effectively if I know some charge flies, its total mechanical energy stays exactly the same. So if you take 2 points, for example, initial point and some final point, the energies, total mechanical energy must be the same. So by comparing those two energies, you should be able to answer some question, or you should be able to find some unknown quantity, right? So we can write, for example, E initial equals to E final, And of course, if you write it explicitly, it will be kinetic energy at the initial point plus potential energy at the initial point equals to final kinetic energy and potential energy at the final point. And of course, I can remind, but of course, usually all students know and remember that kinetic energy, it's a 1 over 2 mv squared, and this is energy of motion. Potential energy, it's an energy of interactions. This is potential energy, energy of motion, kinetic energy, energy of motion. So, and we're going to use this a lot. Okay. And this approach I usually called as the energy approach. So the previous approach where we used Newton's second law, forces, and then kinematic equations, I usually call it like a force approach. And this is the energy approach. Right? Okay, so if you have any questions, you can state, you can ask them. Otherwise, I'll move to problems. Right. So first one, 25.1, it's still chapter 25. 25.1. So what do we have here? Capacitor and a charge inside. Actually, it's a electron, point charge electron, right? And okay, probably I will draw it first. Yeah. Right. Should be enough. Right. So this is a negative electrode, and this positive electrode. Right. Of course, there will be electric field. Let me draw immediately so that it would look nicer. So that's electric field and an electron. An electron is released from the negative electrode. So somewhere over there, there is an electron and it is released. So initial velocity is 0. Let me draw it. So this is an electrode. I mean electron. E minus. Right? And released. So, and this is our initial point, right? So then, what does this this electron do after its release? Of course, it will be repelled by the negative electrode, attracted by positive electrode. So of course, it will start moving that way, accelerating. So we will have to find, I think, the final velocity of the electron just before the positive electrode, right? Just before when it's about to collide with the positive electrode. So, so this will be basically a trajectory. This will be our final point near the positive electrode. And now let me write what is given. So basically, I showed almost everything on the diagram, but one thing which we will need on this diagram to be kind of safer, let's introduce coordinate system. Right. Let me introduce coordinate system. Okay, let's use S. Why not? S. So this is initial point, S equals 0, and this will be our final point. S final equals to D. Okay, and now let me give you some numbers. So we have an electron, all right, in a parallel plate capacitor. So that's the system. Electric field. Electric field strength is given 20,000 newtons per coulombs. Electric field strength. Then spacing between the plates, D, 1 millimeter. And most likely, that's 1. We will have to convert it 2 meters. Let's do it immediately, right, so that we wouldn't forget it later. So it will be 1 times 10 to the power of negative 3 meters. What else? An electron is released. So it means that the initial velocity is 0, right? So I can write, so V sub I equals 0. What else we can write? Of course, we assume that you know charge and mass of an electron. You just open the book, right, and you can see those universal constants, right? Constants. So what needs to be found? Find the final, right? Okay, so that's the problem. You can say we solved something similar, right? In the second or third recitation class. Yes, we did. But we used the vector approach, force approach. But now we've developed an alternative approach. Again, both approaches can be used to solve exactly the same problem. Sometimes this approach is easier. Sometimes this approach is easier. Sometimes they're both equally easy, right? It's just a question of your preferences, right? You might hate this, or you might like that one, right? So in this case, let's solve this problem using both methods. But first, let's start with the energy approach, since it's a new one, and we want to practice it. So I will put symbol 2, and let's use energy approach. Again, they're equally strong, powerful, right? And which approach to use, it's up to you. Or a person who created a problem and asking you to solve this or that problem using this or that approach, right? And as you probably realize that this approach is not new for you. You used it in Physics 1 lots of times, right? But of course, you didn't have electric potential energy. You have some gravitational potential energy, spring potential energy, right? So, but the idea is exactly the same. But except for, instead of those potential energies, now we have electric potential energy. But the ideology is exactly the same. Or maybe I should say very, very similar. Right? Okay, so it means that we just need to compare total mechanical energies at any 2 points. Since we have some information at this point, so this will be our initial point. And since we want to find something at the final point, that will be the final point in this expression. So let me write it down. So E sub I equals to E sub F. So that's the beginning all the time of this approach, which is compare total energies at any 2 points, of course, can be used. But of course, since something is given and something needs to be found, so those 2 points are the most convenient. So let me write now explicitly. It's a K kinetic energy plus potential at the initial point and kinetic plus potential at the final point. Kinetic energy is here. Potential energy, guys, careful which formula to use, because on the final exam or some exam, when I give a problem like this, some students just grab whatever formula is closer, right, and use it. No. We have a charge inside of a capacitor, so we have to use this. Right. So of course, potential energy, let me write over here, it's Q E times S. Don't use anything else. Okay, so let me write explicitly everything in this. So it's a 1 over 2 mv initial squared plus qes initial equals. And now let me just repeat exactly the same for the final point. 1 over 2 mv final squared plus qes final. Okay, and now we can apply what is given, so immediately to simplify, right? Because too many terms. First, initial position, S initial. The object was released from the negative electrode, and that's where our origin is, S equals 0. Remember that S in this formula, it's a distance from the negative electrode to a point where the charge is. In this case, at the initial point, S initial is 0, right? So that is 0. Then, initial velocity. also 0 because the object is or was released, right? V initial also 0. Right? Or immediately we simplified significantly. And what needs to be found? V final here. So that's our unknown. Right? And S final, of course, it's a D. Maybe I can write. So S final, it's a D which is given, spacing between the plates. So basically, given, unknown, given. Everything is given except for V final, one equation, one unknown. Basically, from the physical point of view, we almost solve it. Now we just need to massage it a little bit and get expression. Right. So let me first move them to different sides. Right, V final squared equals to minus Q E D. Right. And now we can get, of course, V final squared. It will be equal to minus 2Q E D over M. And V final equals square root. Okay, it will be minus 2Q E D divided by M. Of course, it should trigger immediately some alarm. Whenever you see minus under the square root sign, of course, kind of, okay, we have to be careful. Right? We don't want to go into the imaginary quantities, right? Because here it's just a velocity, it's nothing imaginary about that. But of course, we need to remember the charge is negative. It's an electron, right? So of course, I can write it, for example, like this. It will be square root of negative 2. And then I can write minus Q an absolute value, right? So to explicitly show that minus D divided by M, right? So as a result, of course, we're getting the formula without any minuses. Square root of 2, absolute value of the charge, E D divided by M. Right. D we already converted into meters. Here, just the absolute value of the charge, so don't have to use minus, or use this formula, and then, of course, you can use negative value of the charge here in this formula. Right? Right. So if you plug mass of an electron, of course, I can give you, but you can find it in the book. 911 times 10 to the power of minus 31 kilograms. Usually I don't give these numbers because you can open the book and you can see those values. So as a result, V final will be equal to what? What's the number? 2.7 times 10 to the power of 6 meters per second. That's quite a speed. That's quite a speed. It's basically 2,700 kilometers per second. It's quite a speed. But of course, for the world of elementary particles, it's nothing. It's normal, right? Basically, we have like a simple accelerator of charges. Over 1 millimeter, this electron accelerated from 0 to 2,700 kilometers per second. It's quite an acceleration, right? As you can imagine. Okay, so that's the approach. Nothing fancy, right? You shouldn't have any significant troubles with that. But of course, if you need more explanations, yeah, can talk more. So now let's solve it using a force approach, because I told you sometimes this approach is easier, sometimes that approach is easier, sometimes they're both equally easy. Okay, so let's just for fun, let's look at the approach number 1, force approach. So where, of course, we use forces, Newton's second law, and then, of course, naturally, under certain conditions, we can use kinematic equations. So let's do it. So let's start with the force. And now let me use vectors. Right? Because now we have to take care of directions. That's the disadvantage of dealing with vector quantities. Right? So, of course, QE, right? So that's expression, formula for the electric force. And charge is negative. So let me show that minus explicitly. Right, so it will be equals to minus absolute value of the charge. Then electric field. Electric field, you see, points that way. Negative S direction. So of course I should write it like this: E times I. Okay, let me use minus I hat direction. Okay, I hat, it's basically X direction, right? Okay, I used it for this S, right? It's not a big deal, right? So I just wanted to show the direction of E is negative. So we have minus here, minus there, plus. So it will be absolute value of charge times the absolute value of the electric field, and now just in the positive S direction. Does it make sense? Of course it makes sense that force points that way, because basically this force accelerates this electron, because our electron accelerates and accelerates that way in a positive S direction, and that's what we got. Force pushes object, an electron, that way, right? So positive direction. So now, of course, after this, Newton's second law, right? So F equals, yeah, I can use still ma, and of course acceleration will be equal to force divided by the mass. So we just need to divide that by the mass, not a big deal. So it will be absolute value of the charge, E divided by m, and in the I hat direction. Again, acceleration is in the positive S direction, as it should be, because again, electron accelerates that way. So next, acceleration is constant. It means that we can use kinematic equations, right? So it's a constant. So it means that kinematic equations can be used. Kinematic equations. Which one? There are three of them. But since no information about the travel time, since the question is not about finding time, it's a clear indication that the equation number 3, or no time equation, probably will be the most efficient. So let's try to use it. So which is v squared equals to v naught squared plus 2a, and okay, it's not x, we have s. All right, S final minus S initial, right? So this is the final, probably instead of 0, I should use initial, right? Yeah, like this. So this is 0, S initial 0, and we just need to take a square root. So the final will be equal to square root of 2. Instead of acceleration, I will use this. So it will be absolute value of charge times electric field, and divided by m, and then this SF, which is d, should be added here. So look, we're getting exactly the same expression, right? So exactly the same thing. So as for this problem, both methods are trivial. Both methods are easy, right? So I cannot say that this is better or this is better. Again, the only difference that here you have to take care of the directions, right? That's it. But the next one, next example. Okay, guys, clear? Of course, we will practice more problems of this type. And most likely, these will be on the first midterm exam. And again, you've done problems like this in Physics 1. So let me erase. Yeah, I need to erase this, start erasing this. Probably from this point, I will start erasing. So next one, okay, this problem is not from the book. I just picked it, I don't remember, right? And I liked it, so I decided to use it. So I will just put a new bullet. So just a problem. And now we have this situation. Two electrons. One is fixed. It means that I'm just holding it. Or maybe you nailed it right to the wall, right? So maybe at some point it wants to fly. Maybe it desperately wants to fly away, but it is stationary. So it cannot move. The second electron is shot from some distance towards the first one. Of course, they're going to repel each other because they're both negative charges. They're both electrons, right? So of course, as a result, this electron will be decelerating, right? Decelerating. And at a certain point, of course, it will stop for a moment, turns around, and start moving or flying in the opposite direction. So we need to find this shortest distance between these two electrons. Again, the first one is stationary. Again, of course, it desperately wants to fly away, but well, it is being held. So now, let me draw the situation and start discussing it. I don't want to erase this because now, obviously, I will have to use this formula and I want to see it in front of my eyes. But okay, you have in your notes, right? And of course, I remember. So now we have a system of 2-point charges and this formula we'll have to use. So first problem was about the system which I just erased, charge in a capacitor. And now the second problem about the second system. Okay, I will start erasing this. You have in your notes. And maybe I'll use, this will be my blue electron. Let me estimate the amount of space that I might need. Yeah, so that's electron number 1. And here will be electron number 2. And this is, I'll emphasize, stationary. So then, as I said, at initial moment, the distance between these two electrons is R1, 1 millimeter. Then this electron, the second one, has initial velocity v naught, 1 times 10 to the power of 3 meters per second. So 1 kilometers per second. So again, this stationary at the initial moment of time, this flies with this velocity. And as I said, of course, it will travel for some distance and then it will stop for a moment and start flying in the opposite direction. So we need to find, as I told you, this distance R2, the shortest distance between these two electrons. So what can we tell about the velocity, final velocity of this second electron at this moment? Of course, it's a turning point, right? You remember physics 1, where velocity for a moment is 0. So I can write that this, which way I label it, final. Okay, so this will be my V final. V final equals 0. You know what, then let me switch this V sub 0 to V initial to be consistent. V initial. Still I use R1, R2. Okay, it's not a big deal. And what else I need to show to you? Let me check in my notes. Yeah, I wanted to write, so here it's the initial position. So initial. And this is final. Okay, so now everything is on the board. Again, two approaches can be used. Energy or force approach. Again, since energy is the new one, let's start with the energy approach, and then we will look at the force approach as well to see which one is better in this case, in this situation. All right, so let me put 2 and energy approach. Which is based on conservation of mechanical energy. So immediately I can write, so E, which way I wrote it, E sub initial, okay, E equals to E sub F, right? Typical beginning. Now let's write explicitly K plus U, K plus U. K initial plus U initial equals to K final plus U final. And of course, at this point, make sure that you use the correct formula, because as I told you on some exam, on the final exam, I've seen students using just wrong formula. Here we have 2-point charges, and of course we have to use U equals K 2 electrons. So effectively it will be Q times Q over a first power of R. So it will be K Q squared over R. That's what we have to use. Don't use the wrong formulas, right? So now, as I said, let me write explicitly. So it will be 1 over 2 mv initial squared plus 1 k q squared over r initial, it's r1, then 1 over 2 mv final squared plus kq squared over r2. Okay, now let's dump what is 0. What is 0? Initial velocity is not 0. Final velocity is 0. So this can be dumped. Then, oh, nothing else. This is not 0. This is not 0. Yeah, damn it. Disappointing. Only one term can be dumped. And now let's count it. How many unknowns do we have in this equation? Mass, it's an electron. Open the book and you can see that number. Then initial velocity is given, charge is given, R1 is given, this is given, charge is given, R2 is not known. Right? So one unknown only. One equation, one unknown. What else do we want? From this point, it's only mathematics. So we just need to solve it for R2. At this point, physics is over. Right? So what I'm going to do, I'm going to, of course, this is 0. I'm going to divide the whole equation by kq squared, so that this kq squared disappeared and kq squared will appear in this term. I just want to free unknown from any factors in front of that. So I'm going to do this. I'm going to just multiply the whole equation, but by 1 over kq squared. Basically dividing each of these terms by kq squared. Again, the goal is to free unknown from any factors. As a result, we will have mv1 squared divided by 2kq squared. This will be just 1 over r1, and here I will have only 1 over r2. Okay, unknown is over here. So now we just need to flip the whole thing, right? Take a reciprocal, and as a result, R2 will be equal 1 divided by the whole this structure. So it will be, let me write first 1 over R1 plus mv1 squared over 2kq squared. Just the whole thing, all this term, all this construction now is in the denominator. Right? I just took a reciprocal. So that's the, okay, I can reduce the size of that. That's an algebraic equation, expression. Everything is given. Again, don't forget to convert these to meters. So R must be in meters. All right, and as a result, if you plug numbers, which I'm not going to do, you will get 3.4 times 10 to the power of negative 4 meters. You see, it's in terms of algebra a little bit more complicated than here, right? But for your level, it shouldn't be a big deal, right? Otherwise, approach is very, very similar. Okay, so now that's the energy approach. Let's see what can we get out of the force approach. So, force approach. Okay, now of course it's based on the electric force and Newton's second law. Uh, of course, electric force, it's a K q squared over r to the power of 2. Of course, now it's r to the power of 2. It's basically Coulomb's law. Not basically, it is a Coulomb's law. And q squared because we have two identical charges. Then, of course, we need to plug it into Newton's second law. F equals ma, right? Mass times acceleration. And of course, as a result, acceleration, I can write it will be F over m. So just mass goes into this. It will be kq squared over mr squared. Okay, and at this point, I need to pause and ask. So what do we usually use after this? Like in this energy, in the force approach. Once we get acceleration, we move to kinematic equations. Can we use kinematic equations now? Can we use any of the kinematic equations now? And I'm sure that most of you know the answer, right? I see somebody posted. Okay, yeah. Of course, somebody posted in chat, no. Of course, it's no. Because now acceleration is not constant. Acceleration is a function of r. Look what happens with r as these electrons travels. It's getting closer and closer to the electron, and r is getting smaller and smaller and smaller and smaller and smaller. R is, acceleration is the variable. It changes with position. So as a result, acceleration is not constant. We cannot use kinematic equations. It means that, okay, so let me first write that. It's not constant. Let me emphasize what makes it not constant, this r. As a result, kinematic equations cannot be used. Kinematic equations cannot be used. Of course, it's not the end of life, not the end of story, right? Of course, basically it's a second order differential equation. Solve it. Now it's a, of course, what is acceleration? It's a r double dot, right? So in this case, it will be a second order differential equation which needs to be solved. Of course, it can be done. So it must be integrated. So it, okay, it's a mess. So it must be integrated. Oops. Integrated. Of course, we're not going to do it. It's a more complicated. I will just wanted to emphasize, so it's a more complicated. Difficult to write here. The goal was just to demonstrate in this example, both approaches were equally easy. Here, energy approach is easier than the force approach. Of course, the energy approach is here preferable to use, right? Frost out equal sign here. Guys, you can
It's at the second, yeah, right there.
Constant. Yeah. Okay. It looks like M, right? Okay, it's a constant. Somebody clarified. I see constant. Yeah. Okay, guys. So that's just wanted to compare two methods. Of course, introduce the new one, okay, relatively new one approach, and of course, compare with the previous one. Right? Again, you cannot tell the recipe this is better than this one. No, it depends on the problem. It depends on the situation. It depends on skills, right? Maybe all possible situations are possible. So now, next one, the last one. The next one is reasonably easy, and I remember after solving this problem for maybe a couple of semesters, I decided to skip solving in classes. But then I started getting emails from students, and they were confused and they didn't know how to handle this problem. So as a result, I decided, okay, no, it's time to bring it back, and we're going to discuss it in our recitation classes. 25.6, and something similar will be in your homework. So we introduced all those formulas which I erased, right, for a system of two objects, right? Two charged objects. But what if we have more than two objects? What instead of 2-point charges, we have 3-point charges? How can you calculate total potential energy of the system? Okay, so let me draw the situation. So over here there is a positive charge, then somewhere up here there will be negative, and this is negative, and they form an equilateral triangle. So all sides are equal, so L, L, L. So then Q1, this Q1 is what? 1 nanocoulombs. No, that's ugly. Nanocoulomb. Then this Q2 is negative 2 nanocoulombs, and Q3 also negative 2 nanocoulombs, and L is given. L is 3 centimeters. Of course, you'll have to convert it to meters. Or maybe I can write immediately. So it's 3 times 10 to the power of negative 2 meters. Okay, so of course the problem is we introduced formulas for 2-point charges, right? This, right? Q1, Q2, 2-point charges, but now we have more than 2-point charges. Then ideology is very simple. So you just need to count all possible pairs of charges and use that formula as many pairs as you have in a system. So of course you have first system, first pair of charges, Q1 and Q2. Then, of course, there will be these Q1 and Q3, second pair of charges, second expression. And then, of course, these guys, Q2 and Q3, the third pair of charges, again giving us their contribution to the total potential energy. So we will just have 3 terms, right? So U total of the system, total potential energy of the system, will consist of 3 terms. U1, 2, okay, it's that first pair, potential energy created by charge Q1 and Q2. Then potential energy created by 1 and 3, let's say. And then, of course, potential energy created by a pair of charges 2 and 3. And then, yeah, write explicitly using that formula which we introduced. So, okay, Q1, Q2 divided by, in this case, L squared, right? Because the distance is L. For each of these terms, the distances are exactly the same. And of course, some of these charges positive, some of them negative, making our potential energy positive or negative. So don't be afraid of a negative potential energy. It's nothing wrong with that. plus k q1 q3 over L squared and plus k k q2 q3 over L squared. So as simple as that. In this case, two terms are going to be negative, one is positive, but if you add them up, in this particular case, the total mechanical, or the total potential energy is going to be zero, right? Okay, maybe I will write the answers. Okay, I will just write immediately, 0 joules, right? In this particular case, it will be 0 joules. You can plug numbers. So because the problem is so, I thought, kind of not that complicated. So at some point I skipped solving it, but then I started getting emails from students, how should we handle this problem or that problem? So I decided to put it back. Okay, so that's what I planned for today. Guys, if you have questions, we can spend a few minutes. All right, yeah, like 4 or 5 minutes. If not, then I will see you tomorrow. Again, tomorrow there will be a recitation class as usual because it's Wednesday, and I will have to lecture at the very beginning, like maybe like for 15-20 minutes about the electric potential, because the next lecture will be only on Thursday. We don't have a material to discuss. Right, so first there will be a short lecture and then problems.